So you see, it's not a problem anymore. But if you don't think about it, it actually is a problem. Now, by the way, are there any other boundary conditions that would do this to you? And in fact, there are. So suppose I had this, but now at the boundary, I impose something like the normal, the no-flux boundary conditions. Okay. So first of all, I could say, well, we know if we have a solution for this equation, then you could say, well, I could also, remember, add. Yeah, I ditched the periodics, and I'm going to replace them now with no flux. And I could say, okay, now I have this, and if I have a solution, I could always add this to it. But by the way, do these satisfy the boundary? And by the way, if you take the flux across the boundary in x and y, these won't satisfy the boundary. But if you take a derivative, the boundary C does. So this is still a solution. And same thing as before, we built that matrix A to contain periodic boundary conditions. If you built that matrix A to do no flux boundary conditions, same problem arises. And then you have to desingularize that matrix. Those are the only two boundary conditions. So for instance, some people would apply not no flux, but let's do one other boundary condition. Pinned. Stream function is 0 at the boundary. Well, now you can't just do anything here. Like, in fact, these all get pinned down. This here? No. This is imposing 0 at the boundary.
But isn't it periodic? You put 0 and then...
Very different.
So that matches that.
Very different. So that one there does not have to be 0 at the boundary. I can have something here. It has to be the same over here. It could be that the solution goes to 0 there, but if something comes out here, this just enforces. This thing is like pins it down. That here kills everything.
But if that's true, that C is 0 at all boundaries, then it's not true that C at one boundary equals C at another boundary?
Not in general. This, no.
Well, no, I mean, I'm not saying that that's the same as that. I'm saying that is a subset of that.
Yeah, so imposing 0 at the boundary here locks in a C. So, right? So saying this here, if you have this on the boundary, doesn't make C 0, it just makes C a number. Because remember, you found a C naught, a psi naught, which doesn't enforce the boundary. You have to pick the C right to enforce the boundary. Yeah. Okay, so no flux, periodic boundaries. When you have this Poisson equation, in those boundary conditions, you have this issue of singularities. And you have to take care of it. Okay? But it's really easy to take care of. And, moreover, it really doesn't affect the physics of the problem. That's very important, right? Because you start playing games like this, like, wait a minute, I have an infinite number of solutions, and does that mean I have an infinite number of things that can happen in an atmosphere? No. Because all you care about is the derivative of that function, and that constant C goes away. Okay. So for us, it becomes rather trivial. Now, let's talk about this now. That's one way to take care of it. The other thing now we did is we talked about, so for many of the methods we did, we talked about setting this up in terms of AX equal to B. But then we talked about doing Fourier transform. Shouldn't the Fourier transform have the same problem? This has nothing to do with a numerical technique. This is just the fact that you've set up a problem that has an infinite number of solutions. And isn't it true that if I were to solve this problem using Fourier transforms, shouldn't I have some kind of problem like that? The answer is yes, but how it manifests itself is very different. So we come back to here, periodic boundary conditions. And what we're going to do is we Fourier transformed last time. And if you remember what we did in class last time, this is the fast Fourier transform method. We found that if you Fourier transform in both x and y, you get the following relationship. Fairly simple. Awesome. You say, hey, I Fourier transform this in x and y, my vorticity, divided by kx squared plus k squared minus sine, inverse Fourier transform. Done. See any problems there? Well, kx and ky are the wave numbers, right? Remember that these are things that are like this. There is a DC component to this, DC. So these are frequency components, right? And then if you think about kx being 0, right? Either 0, this is just becomes 1. This is like your DC field, okay? And most signals have some DC component, and then you take things out. So we can just ask the simple question, what happens when you look at this kx or ky when they're 0? Who loves to divide by 0? Because MATLAB will complain to you. So the manifestation of this problem about singularity in the Fourier transform shows up as a divide by 0. Okay? If kx and ky are 0, you have the divide by 0. And the summary of that is that it is bad. Okay. Frowned upon by many. Okay. And this ultimately reflects the same issue as before, which is if you didn't have a problem here, if you didn't have the divide by 0, you'd say, well, look, I have somehow this idea that there's an infinite number of solutions has to manifest itself. This is how it does it. How do you handle this now? Because before we just took a matrix component, put 7 in there, boom, done. Now we have to take care of this. All right. A couple ways to do it. I'm dividing by 0. That's kind of a problem. What if I were to put something that's not 0? It's my Zoolander, not 0. Okay, so, right? That's 0, but it's not, is it? I mean, really, it's small, but not 0. And by the way, you kind of go, well, wait a minute, you can't start doing stuff like that. You just made an error. Yeah? When I go to solve this with OD45, what's my accuracy? I'm just going to step forward using OD45 without doing anything else. The accuracy it guarantees me is 10 to the minus 6. So I'm doing something here that's 8 orders of magnitude below that. I have errors that are far bigger just in one time step of OD45. All I want to do with this is when these are 0, this ensures that I don't have a divide by 0. It has no problem dividing by 10 to the minus 14.
So you're sure that they're multiplied and build up through?
No. Well, a lot less than if you time step it. Right? 8 orders of magnitude less. So this is one way to do it. Just say, when I divide, I'll just put this little bit of here, and then when these are 0, it says, okay, they're small. It gives me a big number, but big deal. I can handle that big number. A more common way to do it is to say when you build these kx and ky's, which are your wave vectors, turns out that kx1 is 0 and ky1 is 0. These are your 0 components that you worry about. So one very easy way to handle then the transition is either you could do this here, but then this affects every single component that's here, right? So I'm going to divide by all the wave numbers, and everyone takes a little bit of a 10 to the minus 14 with it. Leave it like that, and just put it where you need it, is when these guys are 0. So instead of these things being 0, just do this. I'm just making this up, something like that, 10 to the minus 6, for instance.
Why just make it 0? If you make them 0, isn't that equivalent to saying the boundary condition is 0 everywhere?
So if you make these 0, no, this is a wave number 0, and you're going to get a divide by 0. You'll be in trouble.
No, I mean the waves. The Fourier series is a bunch of coefficients
Yep.
times something, and the DC component, the 0 coefficient has a weight, and if that weight is 0, doesn't it mean...
No, this is not. No, we're not making the weight 0. It's the wave number that matters, not the weight. So, right, you have...
Right.
Right?
So you're not making...
No, you cannot make this 0. That's a problem. This is like a resonance condition about the frequency itself. So this you don't want to touch that. If you zero that out, you're making huge, because this thing is not near zero at all. But it's the combination at the zero frequency. What is the weighting? This guy here is what matters if this can't be zero. Okay? And then you don't make it zero. You make it small. 10 to the minus 6. By the way, when you square it, it's 10 to the minus 12. Okay? So that is about the order of magnitude you're making things on. And by the way, making it 10 to the minus 6 is on the same order of magnitude as what you're typically doing with stepping with OD45. So that's why I picked that. So you make that 10 to the minus 6. Everything's good. When you come to divide here by zeros, they're not zeros. They're 10 to the minus 6s. Problem solved. And we'll show this in class.
So you can't change the DC coefficient.
No.
The weight.
Don't change this. Just make this 0 plus a little bit. Okay, so this is the equivalent of putting a 7 in that position. Because you know what this does here? Whatever you pick this number to be, or if you put 10 minus 14 there, this locks in that constancy. Whatever you pick here, just picks a constancy, essentially. Okay? If I put this to be 10 to the minus 5, it's a different C. If I pick it 10 to the minus 4, a different C. 3 times 10 to the minus 6, different C. Do we care about the C? We don't, because all we're going to do is take derivatives of this thing anyway. Okay?
Sorry, so then the other thing, putting a little extra wiggle on the bottom of that the denominator, if that's a legitimate method, it's not as good, or it's...
Which one here? So you could, you know, the thing that's not quite as nice about this is even when you don't need to have it, you have it now, right? So here, you're only putting it on the things that are creating the problem. So here you're putting it everywhere, whether you need it or not. Here you're just saying, only when I need it do I put it there.
But would it work, or is it
Yeah, both work. This one here, I find this one to be a little bit better, or you can just bring this up to 10 to the minus 12. If you make it 10 to the minus 14, it starts getting pretty close to the round-off floor. Makes this really huge, makes it a little bit not as nice to work with. So this is more what people adopt in the literature. They don't typically do that. They just say, do this, so we only put errors in at the spots that are problematic. So there you go. And by the way, you only need to do this for the wave numbers that related to this stream function solve. Remember, when we're going to actually solve the whole vorticity dynamics with Fourier transforms, and there we have Laplacian again, kx squared, ky squared, but they don't show up in the denominator, in the numerator, and then we don't need to do this. Okay? This is only because we have the denominator problem.